Hello students, in previous lecture we have studied detailed about the transition elements and the metallurgical processes in which iron is extracted from its ore in blast furnace. Then we will now study detail about the inner transition elements. See here, all of you studied the periodic table in 11th standard. Then inner transition elements are F block elements. See here, inner transition elements, which is also known as F block elements. That means the concept of F block element or inner transition element, the element in which n-2f orbital, that is per penultimate f orbital, per penultimate, that means n-2f orbitals are gradually filled up or progressively filled up. That means the elements in which n-2f orbitals are progressively filled up, that elements are called as inner transition elements, or that elements are called as F block elements. All of you studied about that. Inner transition elements are present in two series. That means there are two series of inner transition elements which is placed at the bottom of periodic table for the study of these elements conveniently or easily. Then see here, these two series, all of you aware of that, these are lanthanoids and actinoids. That is, first lanthanoids, in which there are 14 elements. See here, there are 14 elements after lanthanum. That means lanthanum is not considered in it. 14 elements after lanthanum are called as lanthanoids. These are called as lanthanoids. And lanthanum, that having atomic number 57, to lutetium, these are comes in this series, in lanthanoid series, or it is also known as 4F series element. 4F series elements, that is first inner transition series elements, which is present in 6th period in the periodic table. Then see here, one more series is there, that is second inner transition series, which is known as actinoids. Similarly, lanthanoids, the actinoids, the 14 elements after actinium are called as actinoids, which is also known as 5F series elements. That is, here the 14 elements after actinium are called as actinoids, and this series starts with actinium having atomic number 89 to lawrencium 103. That means there are total 15 elements in the second inner transition series elements, and which is present in 7th period in the periodic table. Then see here, the inner transition element which lies between d orbital elements and s orbitals, and these elements are lies deeply into the d block elements, therefore they are called as inner transition elements. That means here n-1d, that is penultimate d orbital, in which 0 electrons or 1 electrons are present in it. That means see here, lanthanoid series and actinoid series, these are the two series which is the 14 elements of lanthanoids and 14 elements of actinoids. These are placed at the same place of lanthanoid and actinoid, that but to convenient to study about these elements, these are placed separately in two series at the bottom of periodic table. Then see here, the lanthanoid series, which is known as 4f series elements and which starts with lanthanum. But here focus on this series, that lanthanum which having electronic configuration in which d orbital is filled and f orbital is empty. Therefore lanthanum is d block element, and the element after lanthanum are the 4f series elements, or generally we can write the electronic configuration, that is valence electronic configuration for all inner transition elements. That is, see here, ns2 ns, that means outermost s orbital which containing 2 electron in it, and n-1 d orbital which having 0, 1 or sometimes there is 2 electrons exceptionally are there, and n-2 f orbital, that is per penultimate f orbital in which 1 to 14 electrons are there. That means n-2 f orbital here gradually filled up. Therefore general valence electronic configuration for f block elements, that is inner transition element, is ns2 n-1d 0 to 1 and n-2 f1 to 14. Then we will study detail about the lanthanoid series. Then see here, lanthanoid series in which total, considering with lanthanum, total 15 elements are there. But lanthanum which comes under the d block elements. See here, lanthanum having atomic number 57, cerium having atomic number 58, praseodymium Pr, Nd neodymium, Pm promethium, Sm samarium, Eu europium, Gd gadolinium, Tb terbium, Dy dysprosium, Ho holmium, Er erbium, Tm thulium, Yb ytterbium, and Lu lutetium. Then see here, lanthanum which having atomic number 57, cerium atomic number 58, praseodymium atomic number 59, neodymium atomic number 60, promethium having atomic number 61, samarium atomic number 62, europium atomic number 63, gadolinium atomic number 64, terbium atomic number 65, dysprosium atomic number 66, holmium atomic number 67, erbium atomic number 68, thulium having atomic number 69, ytterbium 70, and lutetium 71 atomic number. Then you have to remind these all inner transition elements, that is lanthanoids, and then we will write the expected electronic configuration as well as observed electronic configuration of lanthanoid elements. For this purpose we have to write the general valence electronic configuration for lanthanoid first. Then see here, the general valence electronic configuration for lanthanoid, that is here Ns means 6s orbital which having electrons, 2 electrons are there. That means n-1 means 5d orbital in which 0 or 1 electron may be there, and 4f orbital, that means n-2f, that is 1 to 14 electrons are there, and the nearest noble gas for these all, that is xenon, and which having atomic number 54. Using this general valence electronic configuration for lanthanoids, we can write the expected electronic configuration which is based on the three laws, that is Hund's rule of maximum multiplicity, Pauli's exclusion principle, and Akabaugh principle. The electronic configuration which is based on this rule is called as expected electronic configuration. But for the stability, actual or spectroscopical electronic configuration which is different from the expected electronic configuration is called as observed electronic configuration. Then see here expected electronic configuration, and using this general valence electronic configuration, see here xenon which having atomic number 54, that means here the electronic configuration for xenon in which 54 electrons are filled. Then here see here 54 electron, remaining 3 electron out of these 2 electron enters into 6s2 and 1 electron enters into 5d orbital. Then no more electrons are there, therefore here 4f orbital of lanthanum is empty. Therefore that lanthanum is known as d block element because their 4f orbital is empty. Then for next element, that is cerium, which having atomic number 58, electronic, that is expected electronic configuration for it, that is xenon 54, 6s2. Here the electron does not enter into 5d orbital, therefore 5d is 0, and 4f 2 electrons are there. That means as from cerium to lutetium, these are the f block elements in which n-2f orbitals are gradually filled up. Therefore electron does not enter into 5d orbital, these enters into 4f orbital. Then electronic configuration for cerium, that is 6s2, 5d0, 4f2. Similarly, we can write the electronic configuration for next all elements. So here according to the rule, xenon, that is having atomic number 54, 6s2, 5d0, 4f3. Then neodymium having atomic number 60, xenon 54, remaining 6 electron out of these 2 enters into 6s orbital and 5d orbital is empty. Therefore in 4f orbital 4 electrons are there. For promethium electronic configuration, that is xenon 54, 7 electrons out of these 2 is present in 6s2, 5d0 and 4f5. For samarium, it is xenon 54, 6s2, 5d0 and 4f6. For europium, xenon 54, 6s2, 5d0, 4f7. Gadolinium, xenon 54, 6s2, 5d0, 4f8. For terbium, it is xenon 54, 6s2, 5d0, 4f9. Here 4f orbital is progressively filled up from cerium, and similarly we can write the electronic configuration for dysprosium, that is xenon 54, 6s2, 5d0, 4f10. Similarly for holmium, xenon 54, 6s2, 5d0 and 4f11. For erbium, it is xenon 54 6s2 5d0 4f12. For thulium, it is xenon 54 6s2 5d0 4f13. For ytterbium, atomic number 70, xenon 54 6s2 5d0 and 4f14. For lutetium, that is last element of lanthanoid, that is having atomic number 71, xenon 54, the remaining 17 electrons out of these 6s2 5d1 and 4f14. See here, one electron enters into 5d. Why? Because there are 4f orbital is completely filled. Therefore, remaining one electron enters into 5d orbital. That is the expected electronic configuration of lanthanoids from lanthanum to lutetium. But there are some variations which is seen actually in the electronic configuration of their atoms of these elements. Then that electronic configuration is also known as observed electronic configuration or spectroscopical electronic configuration. Then we will study about the observed electronic configuration of those elements. Lanthanum, in which f orbital is empty. Therefore, here xenon 54 4f orbital, that is 4f0, 5d1 and 6s2. See here, the expected electronic configuration and observed electronic configuration for lanthanum is same, in which 5d orbital, the last electron enters into 5d orbital. Therefore, it is a d block element. But the property, most of the properties of lanthanum, it is similar to the lanthanoid elements. Therefore, it is taken in the lanthanoid series. Then it is why? Because the energy of 4f orbital and 5d orbital is nearly the same. Therefore, here one electron is presenting 5d orbital. Then see here, in cerium, observed electronic configuration for cerium is xenon 54 6s2. Here also one electron enters into 5d orbital and 4f1. That means observed electronic configuration for cerium is also, in which one electron is present in 4f orbital and one electron enters into 5d orbital. That is the observed electronic configuration for cerium. That means here the difference in the observed and expected electronic configuration of cerium. Then next, praseodymium, in which xenon 54 6s2, that means 2 electrons are present in 6s orbital in those all elements, and from here 5d orbital is again empty. That means here 5d 0 electrons are there, and 4f, that is here 3 electrons are there. In 4f orbital 3 electrons are there. See here, one more thing, in gadolinium, the observed electronic configuration for it, that is xenon 54 6s2 4f7 and 5d1 is there. That means here, see here, I have written the observed electronic configuration of gadolinium first, because of here 4f orbital in which 7 electrons are there. If 5d orbital, it may be empty, then 4f orbital in which 8 electrons may be there, and because of 1 electron enters into 5d orbital, 4f orbital becomes half filled, that is 4f7 for gadolinium, and this configuration, it is due to maintain the more stability for the element. Similarly, we can write the electronic that is observed electronic configuration for lutetium first. Then see here, for lutetium, xenon 54, xenon 54, 6s2, here also 5d, 1 electron is there in this orbital, and 4f, 14 electrons are present in 4f orbital. Here also 1 electron is also enter into 5d orbital, because here 4f orbital, that is 14 electrons are there, that means 4f orbital is completely filled. Therefore, to maintain the stability, to become more stable, 1 electron enters into 5d orbital. Then see here one more thing, that is in lanthanum 5d orbital possesses 1 electron, cerium which possesses 5d 1 electron, gadolinium possesses 1 electron in 5d orbital, and lutetium possesses 1 electron in 5d orbital, and these all elements possesses 2 electrons in 6s orbital. That means 2 electrons are present in 6s orbital in all lanthanoid elements. 6s2. Then we can write the electronic configuration, observed electronic configuration for these lanthanoids easily. That means here the neodymium which having atomic number 60, out of this electronic configuration for 54 electrons, the electronic configuration like xenon, that means here remaining 6 electrons, out of these 2 electrons are present in 6s2 orbital, 5d orbital is empty, therefore remaining 4 electrons enter into 4f orbital. Then we can write the observed electron configuration for promethium, that is 6s2, 5d0, 4f5 xenon. For the next, that is samarium, xenon 54, 5d is 0, 6s2, 5d 0, therefore 4f6. Similarly, for europium, xenon 54, 6s2, 5d 0, 4f7 electrons are there. Then for terbium, see here having atomic number 65, that is here atomic number 65, the 54 electrons which having electronic configuration like xenon, the remaining 11 electrons, out of these 2 electrons are present in 6s, 5d 0, therefore 4f9 is there. Then for next dysprosium, xenon 54, 6s2, 5d 0, 4f10. For holmium, xenon 54, 6s2, 5d 0, 4f11. For erbium, it is xenon 54, 6s2, 5d 0, 4f12 electrons are there in 4f orbital. For thulium, xenon 54, 6s2, 5d0, 4f, 13 electrons are there. And for ytterbium, observed electronic configuration is xenon, 54, 2 electrons enter into 6s orbital and remaining 14 electrons enter into 4f orbital, therefore 5d orbital, that is 5d0. That is all about the expected and observed electronic configuration of lanthanoids. See here, in observed electronic configuration of lanthanoid, in most of the elements 5d orbital which is empty and 4f orbital which is progressively filled up. Here lanthanum, in which 4f orbital is empty, that means last electron enters into 5d orbital. To maintain the stability, there is for cerium, for gadolinium and for lutetium, 1 electron is present in 5d orbital and 4f orbital becomes half filled for gadolinium to becomes more stable. Similarly, 14 electrons are present in 4f orbital of lutetium and remaining 1 electron enters into 5d orbital to maintain the stability, as last valence orbital, that is 4f orbital of lutetium, it becomes completely filled and make that element stable. That is about the observed electronic configuration and expected electronic configuration of those lanthanoid elements. Now we are going to study about the oxidation state of lanthanoids. All of you studied the electronic configuration, that is observed electronic configuration and expected electronic configuration for lanthanoids. Then see here, their n-2f orbitals are incompletely filled or it is gradually filled up. Electrons enters into n-2f orbital, that is in lanthanoid it is enter into 4f orbital, that means in lanthanoid 4f orbital is gradually filled up. See here the oxidation state of lanthanoid. We will study detail about the oxidation state of lanthanoids. First of all, I am going to clear that the lanthanoid which shows the common oxidation state, that is +3 and +2, that means they shows +2 and +3 common oxidation state, which is the most stable oxidation state shown by the lanthanoid. That means lanthanoid forms the stable compounds in its +2 and +3 oxidation state. Therefore, stable oxides of lanthanoids, it is present in the form of, that is M2O3 form. That means here M is any lanthanoid element, that is for example Ce2O3, in which cerium, which is in +3 oxidation state. That means all lanthanoid, it forms the stable oxides in that form. That is, here we can write this also like Ln, means it is a general symbol or formula for lanthanoids, all lanthanoids from La to Lu, Ln2O3, in which lanthanoids is in common oxidation state, that is +3 oxidation state. Then see here the common oxidation state, that is +2 and +3 shown by the lanthanoids. At first, see here lanthanoid shows +2 oxidation state as well as it shows +3 oxidation state. For this purpose, we have to remind the electronic configuration for lanthanoids. For lanthanum, when it shows +2 oxidation state, it loses 2 electrons from 6s orbital. Then it loses 1 electron from 5d. When it loses 2 electrons from 6s, then it forms +2 oxidation state. That means it forms di-positive ion, that is La2+. And when it loses 2 electrons from 6s and 1 electron which is present in 5d orbital, then it forms the La3+ oxidation state. And La3+ is the most stable oxidation state because of here for this 5d0, 4f0 and 6s0, that means empty field orbital for lanthanum 3+, that is tri-positive ion of lanthanum. Therefore, it is a most stable oxidation state for lanthanum. Similarly, we can write the oxidation state, that is +2, +3, is shown by the lanthanoid elements. Then one more thing, focus here. First 2 electrons from 6s orbital are removed or loosened by the atom of element. Then electron from 4f orbital, it is loosened by it. Then see here, praseodymium, which shows the +2 oxidation state for it. When it loses 2 electrons from 6s orbital, then remaining the 4f3 electronic configuration, 5d0 and 6s0 electronic configuration for praseodymium +2 oxidation state. Similarly, we can write the electronic configuration of 4f orbital for +2 oxidation state and +3 oxidation state shown by those elements. Then see here, promethium, which shows also +2 oxidation state, samarium shows +2 oxidation state, gadolinium, which shows +2 oxidation state, holmium shows +2 oxidation state, thulium shows +2 oxidation state, and ytterbium shows also +2 oxidation state. Similarly, +3 oxidation state shown by lanthanum, cerium, praseodymium, samarium, europium, as well as terbium, dysprosium, holmium, and it is also shown by thulium and lutetium. That is the +3 and +2 common oxidation state, which is shown generally by all these elements. Few of them shows the higher oxidation state. Cerium shows +4 oxidation state, that is the stable oxidation state for cerium. And similarly, few more elements which shows higher oxidation state, but most of the them shows +2 and +3 oxidation state, that is common oxidation state. Then one more thing, that is in their di-positive ion form of these elements, we can write the electronic configuration, as well as in their tri-positive form of these ion, we can write the electronic configuration using observed electronic configuration of those elements. Then see here, for europium, that is EU, +2 oxidation state, and it also shows +3 oxidation state, but +2 oxidation state, that is the most stable oxidation state shown by the europium, as well as here ytterbium, which shows +2 oxidation state, which is the most stable oxidation state shown by those elements. According to the electronic configuration, we can mention the stability of those elements in their di-positive ion form or tri-positive ion form, or +4, that is tetra-positive ion form. That is about the oxidation state of those lanthanoid elements.